with that, I thank you.
Thank you very much. We have time for a few quick questions. Please raise your hand if you have any question. So maybe just to clarify, I can ask, so you don't require anything on the final state of the machine itself. It can be anything.
No, only the final state of the machine can be any, only the final state of the system should be thermal. Yes.
I see. So I see there is a question by Hui Chen.
Hi, very nice talk. Could you briefly discuss the relation between these results to previous similar results? Like there is a recent Nature Physics paper discuss a similar Planckian bond.
I refer to this paper here, a bound on thermalization from diffuse. Yes. So I think the relation is so if you want this the goal of all these papers here on the right is defining some theory of coherent charge transport in metals, and then showing that there is some quantity that is related to the diffusive dynamics of these theories, such as the scattering time of the electrons, or the relaxation time, or the time scale at which some diffusive dynamics appears. So some specifics to these models that is governed by the Planckian time. So it still relies on several notions. For example, the notion of a transport theory of the model that you're looking at. Instead, in our case, it's a bit more adversarial in a way. We just assume that there is some entity, and this entity wants to bring a system to a state that is close to thermal. So in that sense, it's different, but in our case, we don't assume any specific theory, let's say.
Thank you. And another quick question: what's the connection with the metrology you just mentioned?
Yeah, so unfortunately, I had to go very fast. The idea is that from the point of view of the machine receives some input, and it has to output something that depends only on the Hamiltonian of the local system. So the machine, in a way, needs to distinguish different Hamiltonians. If it has to thermalize different Hamiltonians, needs to distinguish different Hamiltonians. So in some limits, for example, in which the machine makes a very small error, this corresponds essentially to Hamiltonian estimation in a sense. And you can connect this to metrology formally and see how this bound can be seen as a consequence of metrology.
See, thank you very much.
There's one more question, maybe very, very quick answer and question. Please, Mohammed. Are you speaking, Mohammed? We can hear you. Your microphone is disconnected. Mohammed, can you hear us?
He's saying in the chat that you don't hear me.
Yes.
Question
so maybe you can ask your question in the chat and we move on to the next speaker. And if you can, please, Paolo, answer in the chat.
Perfect.
As well.
Thank you.
Thank you. Thank you very much. Thank you for the nice talk. And so now we're going to have Alexssandre de Oliveira Junior, who's coming from the Technical University of Denmark and who's going to speak to us about heat as a witness of quantum property. Yes, thank you very much.
Yep.
You can enter full screen or not full screen.
Yes. Can you hear me?
Yes.
That's perfect. Thanks for the introduction. Hello, everyone. First of all, I would like to thank the organizers for the very nice workshop and also for giving me the opportunity to speak here. Today, I'm going to talk about a work which was done in collaboration with Jonathan Borbrask and Patrick Lipka-Bartoshik. The way that I divided this presentation is mainly in two parts. First, I'll state the problem that I would like to discuss. Then I'm going to give just a gist of our results applied to one of the instances of the problem that we solved. As I said, I would like to start with a general question that captures the main essence of this work, namely the question that we were interested. So basically what you're interested can be captured by this first question here. How can we detect quantum features thermodynamically? And as I said, this is a very general question, and in principle, there are many different ways of answering it. However, I also would like to take a more general approach, just as Paulo was discussing, in which we don't make any assumption about the process per se. This means that suppose that we have some system prepared in some unknown state, and we assume that this system undergoes an arbitrarily thermodynamic process. Then, if we have access to the statistics of this experiment, so the relevant thermodynamic quantities such as the heat flow, what I would like to know is whether we can witness the presence of quantum correlations such as entanglement or coherence just by probing this thermodynamic quantity. But I also would like to do this in an experimentally friendly way. So in this work, we managed to do precisely so. We managed to derive a set of quantum properties heat-based witness in which if these inequalities are violated, this means that the state that you are trying to probe possesses this property that you are interested. So in what follows, I will just sketch this very general scenario that we consider, and I'm going to apply this for witnessing the presence of entanglement. So the starting point consists of assuming that we have a composite system comprised of a multipartite system interacting with some thermal environment. This thermal environment is prepared in a thermostat at some inverse temperature beta. And we also will consider that this process is assisted by a quantum memory. Well, the only assumption that I will take is that the joint system is closed. So they evolve under the action of this unitary here, and that this unitary is energy preserving. So I'm making no assumption about the interaction strain, whether it is weak or strong, the complexity, local or collective, or the duration of this protocol. And since we are dealing with energy preserving unitaries and we don't have a drive, we don't have a battery system, this means that the energy exchange in this process can be fully accounted as heat. Well, we will assume that this memory, the state of this quantum memory here, is fixed by the dynamics. This means that initially I prepare the state of this memory in some general state, then I turn on this unitary, the process go on, and at the end of this process, this memory returns exactly to the same state as it started. So in other words, the idea is that the memory will induce some interesting dynamics for the system, but will not change the energetics of the joint system environment. Also, this means that there will be no heat flowing from this memory to this joint system in these two snapshots that I will be looking at, this initial and final time scales, let's put like this, of this process. So then the natural question is why then we are considering quantum memory to assist this process. And being completely agnostic, I could tell you that this memory will allow us to perform transformations which would be otherwise impossible, such as access correlations which are locked on non-degenerate energy subspace, which will contribute to this thermodynamic quantity that we want to probe, which is the heat exchange in the process. And my last assumption of this protocol is that, well, we wanted to probe then this energy exchange, which is the heat which flows in this process. But if I want to attest if this initial state has some entanglement, this means that I cannot measure the system initially and then let it to evolve and measure after, right? Because otherwise I would disturb the system. So what we do is to assume that, first, since this interaction is energy preserving, then I can shift this measurement to this environment, which I will not fix. So this can be just a thermal ancilla. So this means that I can probe this heat exchange by just measuring this environment. And the measurement that I can apply here can be completely general. It doesn't need to be a complex measurement. Within the scenario, the main question that we asked was, what is the optimal heat flow that can happen in this circumstance when we don't put any constraint on anything? And our results are such that we managed to derive a very nice analytical expression for this heat exchange, but I will skip this and focus on the main question that I posed at the beginning of my talk. And to do so, I'm gonna, instead of assuming that we have a multipartite system, I will consider just a bipartite system to illustrate with the entanglement case. Well, so basically, imagine that we have then a bipartite system. This optimal process, which leads to this optimal heat exchange, is when this initial state is mapped to a thermal state at some either inverse temperature beta H or beta C. So depending on the environment or the interaction, the system can either cool down or warm up, but the system will either cool down or warm up to very specific thermostates. Those whose free energy, non-equilibrium free energy, is precisely the same as the initial free energy. And this is the optimal process that you can have in this type of dynamics. And in this case, it is pretty interesting because if we compute the heat exchange in this process, we can show that the heat exchange can be decomposed into two contributions. The first contribution is a contribution which corresponds to a state which has the same average energy and marginal as the state that I'm trying to probe, but this state is separable. So this is the optimal heat exchange, which should be released or absorbed by a separable state with the same average energy and marginal of my initial system, plus some quantum contribution. And this quantum contribution here is just a smooth function of the conditional entropy. And basically what this expression tells us is that you have some advantage if you have the presence of quantum correlations, and this advantage will be captured by when this conditional entropy is negative. If we look when this conditional entropy is negative, we will conclude that this is only possible when this state is entangled. So this means, in a very hand wave way, that our results allow us to write down a hierarchy which puts, in terms of heat exchange, which puts entangled states on the top and product states at the bottom. So this also suggests that we can write heat-based witnesses. So just to give you an example, because I was quite fast over here. So let's imagine that we have the paradigmatic case of an isotropic state. For example, we take some maximally entangled states mixed with noise, which is modeled by this identity here, and we apply our results. So if we plot this optimal heat exchange as a function of this mixing parameter lambda here, we see that the upper curve here is precisely when the system is cooled down, and here is precisely when the system warms up. This is the optimal heat exchange in these two cases. Now, if I ask what is the optimal heat exchange by a separable state with the same average energy and the same marginals as the isotropic state, what we get is precisely these two dashed lines here. So this means that this yellowish area here, this yellowish area here corresponds to this quantum contribution that I showed before. In other words, there are no separable states with the same average energy and marginals capable of giving us this amount of heat here. So this means that if we run our experiment and we probe the heat exchange and we realize that we get this value here, then this means that by looking at our witness, the state is entangled. And then if, as I said, we are able to detect this the presence of entanglement because we rely on the negativity of the conditional entropy. If we plot the conditional entropy as a function of this lambda, we confirm this. So basically this yellow area here is precisely the one up to the point in which this lambda, up to this lambda critical, which is when this conditional entropy is negative. Finally, the last question, and very fast, we could ask what happens for higher dimensional systems since I'm looking only for local dimension 2 here, and what happens with the limit of our detection. And again, if we plot those curves, we see that basically our witness improves with the local dimension. And this is kind of expected because we are increasing the number of, not the number, but the volume of entangled states, right? If we increase this local dimension, and we can detect up to the solution of this NAST equation, but it's easily to solve numerically, which shows us that this lambda critical will increase with the local dimension and saturate. So finally, just let me very quick finalize here by telling that very fast I told you that thermodynamic process can be used as a new type of entanglement witness. And unfortunately, I didn't have time, but we can also use those same results to witness other quantum properties or not necessarily quantum properties, or even the presence of classical correlations by writing down these bounds for the optimal heat exchange. And just a spoiler is that it also gets very interesting when we look at multipartite quantum correlations. With this, thank you very much.
Thank you very much for this very nice talk. Are there any questions? Please raise your hand. Maybe I can ask about this memory, because there is something I didn't quite understand about the use of the memory, especially you ask that it ends up in the same state as it started with. I was wondering, why don't you just ask that just its average energy didn't change in the process?
Yes. So basically, indeed, why we have this memory, it's a bit complicated to understand, but what we can, a nice way of looking at this is, since we are dealing with energy preserving unitaries, it is not so hard to prove that basically the heat exchange the terms which will contribute to the heat exchange are those which lies on the degenerate energy subspace. So basically, by introducing a quantum memory, you can make a bridge to the non-degenerated energy subspace. And then you can bring elements from there to the degenerate energy subspace, and then you can boost your heat exchange. And the fact here is that the memory, indeed, it starts and ends in the same state, but during this state, the state of the memory change, right? It's just that I'm looking at two specific snapshots of my process.
You could have done exactly the same analysis without the memory, but your optimal bound would have been lower in all cases.
Yes, exactly. So basically, in this paper from 2024 of Patrick, he shows that the optimal heat exchange, he derived the optimal heat exchange in the absence of a quantum memory. And for a specific model, he shows that if you allow a memory, you can break those bounds. So another result that we derived here was what are the optimal then heat bounds when you allow some memory system in the process.
Okay.